Yeah, thank you very much, Dennis. Ladies and gentlemen, thank you very much for coming here, and the committee, thank you very much for letting me sharing our results on explosion experiments we have done in a full-scale roller mill. I want to say some thanks to my co-authors, Kai Pedersen and Brian Wilkins from GEXCON, but also Mugens Berg and Niels Otto Nielsen from Vattenfall and Dong Energy, respectively. Vattenfall and Dong Energy are both power companies. Vattenfall is the Swedish word for waterfall, and they started as you may understand now with hydropower. And Dong Energy, Dong sounds like a strange word as well. It just means the Danish oil and natural gas company, so it's an abbreviation. It's nothing special. So there goes everything. Everything what is exotic is gone now. I'm sorry. I want to give you a little bit of background why these experiments were performed. I'll give you a description of the experimental setup, the experimental program. We have done some CFD work to design the experimental conditions we used in this experimental program. And then, of course, I want to share some experimental results with you and end up with some conclusions from the work we've performed. Well, as you know, biomass is becoming more and more popular as a fuel for power generation applications to replace coal. However, grinding of biomass, and the same accounts in fact also for coal, represents a hazard due to the presence of both flammable dust and possible ignition sources due to mechanical sparks, hot surfaces, and smoldering combustion. And this smoldering combustion may even come from the outside, because the material is in fact stored on its way to the mill several locations. First, it is stored in a ship. It's brought to a terminal. Then it's taken off the ship, brought into a huge storage silo, and from there it is transported into another silo again, and this silo is then on top of the mill. So there could be smoldering material coming in from the process preceding the roller mill. But then again, smoldering combustion can also be generated inside the mill, of course. And they've had some incidents. These companies, they had some incidents in the roller mill, and in fact, on the basis of those incidents, they decided to protect the mill against explosions by using suppression, and at the same time isolation also. In fact, there is one ignition source which I forgot. There is a possibility of a back ignition from the burners of the power plant, because the mill is normally transporting the dust, or the dust is directly transported from the mill towards the burners. And if the flow inside towards the burners will be too low, there may be a possibility for the flame running back into the mill. So in fact, they have isolation for that as well. The work that was done to dimension the suppression system was in fact using a maximum overpressure of 0.5 bar inside the mill. They wanted to know whether they really needed the suppression, because if you use the mill, there is always some venting. You got some inlets, you got some outlets, and would it be sufficient just to leave it as it is, so that they only would need isolation? Because they thought that this mill could withstand much more than 0.5 bar. Well, we started doing these experiments on their behalf. We have a site outside of Bergen at the island of Sotra, and they made available, the power companies made available a full-size Lusje roller mill. It was one which was used in the past. It was no longer being used anymore, and the grinding capacity of this mill was 36,000 kilos of coal per hour. That was where it was designed for. Well, the basic parts of the mill are the mill room, and I'll show you on some pictures. The classifier area, which is on top of it. On top of that, again, there is a top with with coal feeder pipe and coal dust pipe. So the coal feeder is in fact where the coals enters the mill, and you've got at the same location in the top, you've got pipes which feed the ground dust towards the burners. This mill on the experimental site was connected to a 5.1 cubic meter coal feeder via a pipe which was 0.6 meter diameter and 3.35 meters long. Some pictures, so perhaps not so easy to see, but this is the area of the mill where the grinding So this is the area where the grinding occurs. Here is the milling table. This is the classifier area. On the top of it, everything which is coarser than what is necessary for the burning is falling back into the milling area, onto the milling table, and is ground again. In the top you see 6 pipes, which are in fact the bits that are left from the burner pipes, so going all the way to the burners. They are typically more than 60 meters long, those pipes. So in these experiments, we in fact put some diaphragms in those pipes to simulate the resistance of the pipe flow due to the length of these burner pipes. Here you see the coal feeder, which is in fact only a sort of a container which we use for representing a coal feeder. And this is the area where normally there would be a big silo on top of that, where the coal feeder, where the material is entering the coal feeder. There is a belt here, which then moves the coal through a pipe into the mill. So between the mill table, in the bottom of the mill, and the mill housing, there is an open clearance, a throat around it. It's called throat, which has a total cross-section of approximately 0.4 square meters. These coal dust outlets to the burners, they are 550 millimeter diameter, and they are, as they were there, as you could see on the picture, 2 meters long. And we put this diaphragm in it to simulate long pipes. On top of the coal feeder, there is an opening which simulates then the connection to the silo, as you saw in the picture as well. And there were also primary air ducts, which are fixed to the mill foundation underneath the mill table, and there the primary air is coming in, which is hot. So here you see some pictures of the inside the mill. This is inside the milling area. You see the big milling wheels. This, in fact, is the ignition source, which we always use constant. Here you see the throat, which I mentioned, between the milling table and the housing of the mill. These are some pictures of these burner pipes again, and here is a picture of the connection to the coal feeder, where we put an opening on it, which we could vary in size to simulate, in fact, the opening of a valve which is there. This, in fact, is offering some venting out of the mill. We wanted, of course, to use the mill under so realistic situation, so realistic conditions as possible. Fortunately, we would need a small power plant to run the mill, and in fact, we could just use the mill itself to generate coal dust sufficiently wood dust to do it ourselves completely. So we would have a small power plant ourselves, but that was too expensive. So we decided to inject the dust as you would normally have in tests, like in a 1 cubic meter vessel in 20 liter sphere, from a vessel which is then pressurized, and then the dust is injected pneumatically into the mill. For that we used 20 liter bottles, which have a fast-acting valve to open them. This fast-acting valve is in fact opened by a torque motor, which allows us to reuse the vessels all the time, so it's easy to refill these vessels. They are in fact part of a suppression system. We did simulations with a CFD code called DESC, from which we chose a 900 millisecond delay time to simulate the I'll say, the worst case operational conditions which could prevail in the mill. I'll show you that in a minute. And then we had a 20 bar driving pressure, and we use typically 1 to 3 kilograms dust per bottle. So here you see the bottles connected to the mill, several locations. Here is a closer picture of one of those bottles. We had 10 pressure transducers regularly divided over the mill. We used video, and we used that was basically it, what we used to diagnose the explosions. We used a 5 kilogram super-igniter, which was positioned 0.65 meters above the center of the milling table. You saw a picture of that. We used coal dust with these properties. So it had a KST value of, it was varying a little bit, 118 to 145. We did several tests during the program to verify the KST value. It is varying a little bit. The dust, moisture content of the dust is low, 2%, which is typical for the dry coal, which is going to the mill, because the mill itself is also used as a dryer. As a matter of fact, by using the primary air, which is hot, it's warm air. The maximum exposure pressure of the dust is 7 to 7.8, and we have a typical medium particle size diameter varying between 55 and 90 microns. It's microns, not millimeters. That M turned into a normal M again. The same happened here. These are the wood dust samples which we investigated, and we had two sources of the dust. From these second sources are in fact coming from power plant, whereas the first dust is coming from a how do you call it, furniture fabrication plant, which appear to be relatively representative for the dust from the power plant as well. Well, we tested this dust from the power plant for every test we performed, and we ended up with three classes. One where the KST value was close to that of the coal dust, one where it was slightly lower, around 90, and one where it was really low, 31 to 55. We determined all these in 20 liter sphere. And the medium particle size diameter is varying, which is the reason why we found these variations in KST value. And also the moisture content is changing. As you can see, it also varies in the direction of getting lower KST value because it's heat sink moisture. These DESK simulations we performed, they were performed with, also DESK is a CFD code to simulate dust explosion simulation code. The starting point of this code was FLAX, which is a dedicated CFD CFD tool for gas explosions. The only thing we really changed was the combustion model. And we use, in fact, equations which are adopted for gas explosions, and we can use those for dust explosions as well, as Derek Bradley showed. The combustion properties are, in fact, directly obtained from 20 liter sphere tests. And there are some submodels in this DESK code which allows us to describe radiation, the effect of radiation on flame propagation, dust lifting, and also explosion suppression. This is the geometry of the DESK simulation. So the DESK simulations were performed to choose the optimum or the most realistic optimum process conditions. We couldn't do experiments with the mill working as it would be used in a power plant, so we tried to simulate that with dust injection. So this is the geometry representation of the mill inside DESK. The aim of this work was just to obtain the turbulence conditions as prevailing when the mill is used under maximum load conditions. And that is basically this 36 tons per hour coal, and at the same time you have then a total airflow rate through the mill of 70,000 cubic meters per hour, which is about 500 grams per cubic meter dust load. Please bear that in mind. We simulated this then with flow through the mill from the primary air channels through the mill, out of the mill again into the burner pipes. And this is then a plot showing the turbulence. In fact, you only have to look at what is inside the mill because we simulated it as it is outside there at Sutra. So there is also turbulence outside here, but only inside. Look at the colors, remember the colors, and if we then do it again with dust injection, you see that the colors are similar. However, there's nothing outside, of course, because we didn't simulate anything outside of the mill. At the same time, there are some differences, but this is the turbulence level after 900 millisecond time delay, and which is close to that what was seen in the other simulation. That's why we chose 900 milliseconds. So now I'm going to share some experimental results with you. We varied the dust cloud size, the location. We varied the dust reactivity, as you saw. We varied, especially for the wood dust, we were more or less forced to vary the dust reactivity. We also varied the dust type because we did both coal and wood, and we investigated some venting parameters. At least those are the results I'll share with you now. Some general observations. We could not do experiments at 500 grams per cubic meter because we saw that we were going to ruin the mill. And we wanted to do a full program. And so we stayed at 350 or lower. That was the maximum concentrations we could run the test with, because otherwise explosion pressures would have been too high. We had some damage, minor damage, and if we would have gone higher, we would probably run into troubles. And we wanted to keep the mill for future programs, if any. We saw big differences between coal dust and wood dust, which are probably due to the dispersion characteristics of the dust, and I'll show you why that is. It looks like coal dust is more raining, whereas wood dust stays more in the air and is easier to disperse, in spite of the particle size distribution being more or less the same. So it's the relative the density of the particles themselves, the fuel itself, which is probably an important parameter for this. In addition to that, we had then these big variations in the wood dust, so that's why we determined the KST value for every single test. Now we want to show you some examples, and fortunately the sound is not very good, so I'll try to get the microphone close to the PC.
I think the speaker is there, I think.
Okay. Are you going to stay there?
Yeah, I will.
I'm going to show you many things.
I do it only for you, Kees.
I appreciate that. But this is the first test where we had a cloud only in the milling part of the mill, and it is coal dust only.
I guess it's coming from here.
Okay. Well, yeah, I'll just take it again. Okay. Well, we can try it once more. Perhaps it's better. No. This is a rather mild explosion. So now we have dust. This test we show now. Dust is everywhere inside the mill. So it's in the lower part where the first one was, but it's also inside the classifier part and in the coal feeder. I think I understand what is going on. May I? No, I want to get out of the presentation. If the sound of this, if we pull that up.
No, that's
there's something else. Is there a sound here somewhere? Here. Oh, it's maximum. Okay. Doesn't work. Okay. It's a pity. Oh, here.
There's a button there. We didn't know that.
Okay, well, it didn't work. Sorry about that. I could as well just keep it over here. It's always nicer when you hear big bangs. As a pyromaniac, I can just assure you that is true. just see where we are now. Yeah, so we saw the difference between having dust only in the low part of the mill, and the second one where we had dust everywhere inside the mill as well, inside the coal feeder as well, and everywhere inside the mill. Here are the pressure measurements of these three tests. One where we had where we had dust only in the lower part of the mill. That is the red one. One where we had dust in the classifier area as well. So the dust cloud was now inside the entire mill, but not inside the coal feeder. And the last one where dust is also in the coal feeder. And you see there is a huge difference. Here we measure up to 1.35 bar inside the mill. If we then look into the coal feeder, the pressure for these three tests, we see that pressures inside the coal feeder are more or less similar, but the behavior of the third one is completely different. And the reason for that is that so if we now move a little bit back and forward, so you see that the explosion runs directly from the mill into the coal feeder through the coal feeder pipe, causes a big bang in the coal feeder. This causes back pressure, so pressure flowing back through the coal feeder pipe into the mill again, whirling up the dust there and causing a stronger explosion in the mill. So if you compare, this is the pressure inside the mill, and you see that here is the pressure occurring inside the coal feeder. So in spite of igniting in the mill, the explosion immediately runs into the coal feeder, causes a big bang there, and that in fact results then later, sorry, the order is not easy. So here is this coal feeder. It results then later into a strengthening of the explosion in the mill itself, which then again results in pressure inside the coal feeder again, which is just pressure running from the mill into the coal feeder. So it gets complex and interesting when you do this. And this is happening in many tests, this behavior. But it's also interesting to see that the coal, in fact, is giving hardly any pressure inside the mill if we have only a cloud inside the mill. And it is completely different from when we have wood dust, because then the pressures are more or less similar in conditions similar to test 9 and test 10, where we have material inside the mill only and inside the mill and the coal feeder. So that this different behavior must be due to the behavior of the particles themselves, the dispersion behavior of the dust. So now we'll see some experiments done with coal dust and with wood dust. So first, this is wood dust, where we have a so this is wood dust, sorry, where we will just vary the dust reactivity. So this is wood dust only inside the mill for every test. And unfortunately, you don't hear the sound. So this is wood dust, low KST value. Then with a somewhat higher KST value, etc. So if we then plot the maximum the maximum explosion pressure measured somewhere in the mill as a function of the KST value, we see this relationship. So we see, as you would expect, an increase of the pressure with the KST value. If the KST value is low, we see big variations and low pressures, and if then the KST value goes up, we see the pressure increases, and that is of course as you would expect. And this was all done for 250 grams per cubic meter, where the cloud was filling the mill only. Uh, I mentioned this difference between coal and wood. Here we see so coal and wood dust, which have in fact more or less the same K value. The only difference is that the K value at 250 gram per cubic meter, where we did this, is lower, or is different between wood and coal. In fact, the coal is more reactive at this concentration than the wood. But in this test, where we had material only in the mill, we see that the wood, in spite of it giving a lower K value, has this pressure going all the way up to 1.7, whereas the coal dust gives hardly any pressure, typically 0.1 bar. And this difference is due to the dispersion characteristics of the dust, because the wood dust stays much longer airbound than the coal dust. The coal dust rains out. We also did some experiments where we varied the vent opening size in the top of the coal feeder. So the coal feeder, which is in fact outside of the mill but is communicating with the mill, there was a vent opening on top, and we varied the size of that vent opening. And we varied it between typically 0.3 all the way up to 0.27, which is the full opening. And you see that, in fact, that vent opening, although it's far away from the coal feeder, if we only have dust inside the mill, has, in fact, quite an influence on the pressure inside the mill. Although it is communicating through a pipe, it has quite some influence on the pressure inside the mill. So venting is important, although it is not venting as you would normally have it. It's venting through its connections through to other equipment. But of course, bear in mind that this was an explosion in the mill only. If we would have had an explosion in the coal feeder as well, which was not the case, although of course some dust will be pushed inside the coal feeder, this picture may have been different. Also, there is this milling table, and there was a throat around it. This throat, in fact, acts as a nozzle, and if the pressure is higher than 1 bar, we get how do you call that, choked flow. And therefore, we see if we have a weak explosion, see more or less the same pressure everywhere. If we have a strong explosion, you see that below the mill table pressures are much lower, as you would expect. Which is also important especially for the user, because they were interested in the possibility of having high pressures in the primary air channels, which are much weaker than the mill itself. Okay, then some conclusions from this work. We have seen pressures being able to go all the way to 1.9 bar. With dust having a K value of 120 bar meter per second, but we didn't have had similar concentrations as you would have under maximum load conditions. For coal dust, that was for wood dust. For coal dust, we see 1.65 bar as a maximum pressure, but again, we didn't use the maximum load conditions. And the important factors affecting the maximum pressure load include then venting possibilities, cloud size, dust reactivity, and dust dispersion properties, as we investigated in this program. Okay. In the end, I want to show you one. Unfortunately, there is no sound, but this is the explosion which caused most damage with wood dust. And well, it doesn't give sound here, so unfortunately, it doesn't work that nice. Hopefully I started it. Yes, it starts. This gives, in fact, the maximum pressures. But the mill is still there. Okay, thank you very much for your attention. If you have questions, then of course I would like to answer them now. And otherwise, you can always send me an email. Simple email address. Thank you very much.